Alright, so let's talk about these troublesome little curves. So let's take a look at this particular reaction right here. So what we've got is bromine, Br2, which is reacting with formic acid to produce several different ions. So if we take this particular reaction in terms of bromine right here, and look at its concentration over time. So what we've done is we started at time 0, so this is the beginning, and then gone for 400 seconds. So during that time, the concentration of bromine went from 0.0120 molarity down to 0.00296 molarity. So if we wanted to figure out the average rate for this reaction, we would just say, alright, so here is the initial rate at time 0, and then it went all the way down to this, so you could figure it out that way. But if we take a look at the graph of this reaction, so if we actually follow it as it occurs, what we see here is the concentration versus time, and we're seeing that the concentration is decreasing as time goes on, which should make sense because bromine is reacting to form these guys over here, so its concentration is going to decrease as it's used up. But the rate at which it is used up is changing. So if we look right here, it's changing really fast. So its rate is, or its disappearance is going pretty quick to begin with. You've got a pretty steep line. Then you come all the way down to the end for the last 100 seconds or so, 50 seconds. We can see that it's not near as steep as it was at the beginning. That means that this reaction has slowed down. So Br2 is disappearing faster up here than it is down here. We've picked 3 points along the way and marked them and written down their exact rate at those particular points. So right here at 100 seconds, the rate at which it's disappearing is 2.96 times 10 to the negative fifth molarity per second. After 200 seconds, so we're at 300 seconds from this point right there, 1.48 times 10 to the negative fifth. So the rate is decreasing as time goes on. And it's decreasing at every step along the way. So really, it's not 2.96 times the negative fifth until it gets to this point, or until it gets to that point. If we move even just slightly from that point, the rate is going to decrease. So it's going to be smaller there, and smaller there, and smaller there, and smaller there. So that means that as time goes on, the rate is constantly changing. So it's not staying at a consistent rate throughout. Okay, so now comes the tricky part then. Good news and bad news. The good news is that the rate at which the rate is changing, so the change that took place from this point to this point, that rate of change is going to be the same rate as change as from this point to that point. So we can calculate what the rate of the reaction is at any point along this line because the rate of the decrease of the rate is constantly changing. Alright, to help us kind of grasp that concept, here's an equation that'll hopefully help us out. So this equation shows the rate with conjuncture with particular concentrations. So what we're saying here is when concentration of A is such and such, and when the concentration of B is such and such, here's what the rate would be at that point. A couple tricky things with this equation then. So first off is this K. So that K is the rate constant. So that's what explains the curve in the reaction, and that's what makes up for that curve in the reaction. So what this rate does then is it says, alright, so here's the amount at which it changes per second that makes it curve like that. And so it makes it so we can consistently find what the rate is at any given point in time on that curve. Also then, the M and the N are the reaction order. So that's going to be a really important concept for this unit. We're going to talk about how you calculate reaction order and then what it means. In a nutshell, what order explains is how much effect the concentration of this guy has on the reaction. So it might be that the concentration of A has a doubling effect on the rate. So increasing the concentration of A greatly increases the rate, whereas increasing the concentration of B doesn't increase it as much. And so this little factor right there is going to explain that change. Also, make sure that you note that this is a rate constant for a certain temperature, so that rate constant will change with the temperature. Also, calculating the units for K is going to be a really important technique for this unit. And you do it just by canceling out units like we've done before. You'll see some examples of that as we go through. Okay, so with that equation, you saw the M and the N. Those tell us the reaction order. And let's look at what those are. So the possible orders are 0, 1st, or 2nd. That means that the values of M or N can be 0, 1, or 2. They can also be fractions and decimals in real life, and that's just because of the way reactions actually occur in the real world. But for our sakes and for calculations, they're almost always going to be 0, 1, or 2 exactly, so whole numbers only. Third order reactions, very, very rare, but there is some that exist out there. There's no such thing as a fourth order reaction. And we'll talk about later why there can't be a third or a fourth order reaction. So with these orders right here, they have different meanings, and there's ways that we would calculate them. But we can only calculate them from experimental data. So what you're going to see a lot during this unit is you're going to see data tables with some information, and you have to be able to compute that information in calculations. So you can't just look at a balanced reaction and figure out what the reaction order is. So just because the coefficient in front of a particular reaction is 2 does not mean that it is a second order reaction. Okay, so they are only found through experimental data, so do not fall into that trap. Alright, so here's what the different orders mean. So if it's a 0 order reaction, if you were to double the concentration of that particular species, it would have no effect on the reaction rate. So here's what this would look like on a data table. You would see a spot where you double the concentration, but you would see no change in the reaction rate. So that means it would be flatlined. First order reaction rate. If you double the concentration of the species, it will double the reaction rate. So doubling the concentration will double the reaction rate. If you triple the concentration, it will triple the reaction rate. If you quadruple the concentration, it will quadruple the reaction rate. That is with a first order reaction. Second order, doubling the concentration will quadruple the reaction rate. So it has a huge effect on the reaction rate. If you triple the concentration, that means the reaction rate will sextuple. Okay, so it has a doubling effect. So reaction order, such as the M and the N right there, they would apply to a single element or compound in the reaction. So A could be second order and B could be 0 order or first order. It depends. We'd have to look at experimental data to find out. But the overall order of the reaction in general, so the whole thing, would be the addition of those particular orders. So if A was second and B was 0, then the overall order would be 2 plus 0, which would be 2. So this whole thing would be a second order reaction. Alright, let's take a deep breath and plunge into the world of kinetics and the rate law. So here we have a particular reaction. This reaction that we're looking at is nitrous oxide reacting with hydrogen gas to produce nitrogen gas and water vapor. So down here we've done 3 completely separate experiments. So this isn't just time 1, time 2, and time 3. This is, we did one experiment with 0.2 molar nitrous oxide and 0.3 molar hydrogen gas. Here was the rate of that reaction. Then we cleaned our glassware and started a separate experiment, experiment number 2. And here was the initial concentration, there was the rate of that reaction. We did a third experiment with new glassware, new equipment, new chemicals, 0.1 molar and 0.2 molar. Here was the rate of that reaction initially. So using these 3 pieces of experimental data, we're going to find the rate law, the rate constant at this temperature, and the overall order for the overall reaction. So in order to do this, we're going to have to look at the experimental data, and we're going to have to do a couple calculations along the way. First thing it wants us to do, though, is find the rate law. So the rate law is just an equation, and it's the equation that we looked at before. So the rate law is rate equals K, which is our as of yet unknown rate constant, times the concentration of NO, and that's going to be raised to some power, so the reaction order, we'll call it M for now because we don't know what it is. And we multiply that by the concentration of H2 raised to its particular power order. We'll call that N for now. So with this particular reaction right here, so rate is equal to K times the concentration of N, the order, H2 to the order. There's going to be no numbers plugged into this. All they're looking for is for us to write out this reaction. The only numbers that we're going to find are going to be this M and N. So this isn't the correct answer quite yet. We need to figure out what M is and what N is, and then plug those numbers in up there. And then that'll be the right answer. So in order to figure out what the order is, we're going to have to do 2 separate equations to figure out what the order is for nitrous oxide and what it is for H2. And to do that, we're going to have to come over here to our experimental data. So the order tells us things like, hey, if we double the concentration of nitrous oxide, what's going to happen to the rate? And so we look over here at our data, and we can see experiment 3 to 1 that we doubled the concentration of nitrous oxide. We went from 0.1 to 0.2, so we doubled that concentration. However, we also increased the concentration of H2 in those experiments from 0.2 to 0.3. So we can't use experiment 3 and 1 to figure out the order of NO, but we can use experiment 2 to 1 because we doubled the concentration of NO and we kept H2 the same. Part of the scientific method in doing a good reaction or a good experiment is that we only have one variable that we're changing. So we can't use experiment 1 to 3 to figure out what our answer is, what our order is, because there's two things changing. There's two variables. We can't have two variables that change. So when we figure out the order of nitrous oxide, the NO, we need to use experiments 1 and 2 to do that. And so we'll isolate just that data and look at it. So what we did from experiment 1 to 2 is we took the concentration of NO and we doubled it. Okay, 0.1 to 0.2, that's a doubling. So then what did that do to the rate then? Well, it brought it from 0.0225 when it was 0.1 up to 0.09 molarity per second when it was 0.2. So we changed the rate when we changed the concentration. So then we would say that the rate, well, what factor did the rate change by? It went from 0.0225 to 0.9. So if we say 0.0900 divided by 0.0225, we see that it changed by a rate of 4, so it quadrupled. So here we go. When we doubled the concentration of nitrous oxide from experiment 1 to experiment 2, the rate at which the reaction occurred quadrupled. So we doubled the concentration, the rate quadrupled. That means the order of this particular reactant would be second order. So that means the little M up there is going to get changed into a 2. So the reaction rate is a second order with respect to nitrous oxide. Here's another way we could calculate that out. So if we, a general reaction or a different general rate would be the concentration factor. So the factor by which we changed the concentration should be equal to the factor of the rate, and this one up here needs to be raised to a power, so we'd find that x, and that x would be the order. Oh man, Mr. Jones, what's going on here? Well, this is what this means. So NO, the nitrous oxide, the factor by which it changed was 2. It doubled. So 2 raised to an unknown power, we'll call it x for now, should equal the rate by which the rate changed, or the factor by which the rate changed. And so the factor of the rate changed by 4. So 2 to the x equals 4. So what would x be in that case? Well, x would equal 2, which means that it is second order, and since it's second order, we put a 2 up there in our reaction rate, in our rate law. Alright, now we're going to do pretty much the same thing with the hydrogen gas. So once again, if we look at our experimental data, we have to pick experiments, so 2 experiments where only the hydrogen gas changed, the nitrous oxide didn't change. And so if we take a look from experiment 3 to experiment 2, we increase the concentration of H2 while the concentration of NO stayed the same. So that means to figure out the order of the H2, we're going to use experiments 2 and 3. So we are using experiment 2 again. That's fine. We're just comparing data. So it's not like we're using any new chemicals. And for this one right here, let's take a look at how the how the concentration of H2 changed. So the concentration started at 0.30 and it changed to 0.20, so it changed by a factor of 1.2. 1.5. So 1.5 was the factor they changed it by. Didn't quite double it. And then the rates, 0.0225, and then it went to 0.0150. And so it changed by a factor also of 1.5. So when we change the concentrations by 1.5 times, the rate changed by 1.5 times. So what does this mean then? If we look at that little general equation I gave you, so we changed the factor by 1.5, raised that to the power of x, and it wound up being 1.5. So that means that x would have to equal 1, because 1.5 to the power of 1 is 1.5. So that means that H2 is first order. So now let's rewrite our rate law with that new information. So rate is going to be equal to our constant K, that we don't know the value of yet, times the concentration of NO. And since NO was second order, we'd put a 2 up there, times the concentration of H2. And since that was first order, we could write a 1 up there, or go ahead and just leave it blank. That's what I'll do. So this right here is the rate law for this particular reaction, and that is complete and correctly written. So rate equals the constant times the concentration, second order, so it's squared, times the concentration of H2. With this information right here, once we know what K is, we can plug in any concentration of NO and H2 and find out what the rate would be at that point in time when those two concentrations are set in that stone. So what the initial rate would be. Okay, so let's move that up there. Now that we know that one's correct, we can hang on to it. And move on to part B, which is the rate constant at this temperature. So now we need to calculate K. So we're going to try and figure out what the K is for these reactions. And this one, it's actually pretty simple, because we can pick any of these 3 experiments, 1, 2, or 3, plug the data in from 1, 2, or 3 into our reaction up here, and calculate for K. So for part B, if we just want to rearrange that equation so that K is equal to rate divided by the concentration of NO squared times the concentration of H2. And so the key is just taking one of these 3 experiments and plugging the data in to this equation right here, and then calculating what the K value is. The nice thing about this, or the one trick you have to watch out for, is you have to use either all experiment 1 or all experiment 2. You can't use the concentration of that from experiment 1, that from 3, and the rate from 2. You have to use the concentration from just one of them. Personally, I'm going to go ahead and use experiment 1, because that's just how I roll. And I'm going to rewrite this then. So I'm going to say that K is equal to the rate in experiment 1. So the rate in experiment 1 was 0.0900 molarity per second. So 0.0900 molarity per second. Hey, it's really important that we write down units when we are calculating for K, because you have to be able to calculate the units for K as well. 0.0990900 molarity per second was the rate. The concentration of NO at that point was 0.20, and we square it. And the concentration of H2 was 0.30. And those are both molarity as well. And if we solve that out, what we're going to find is that K is equal to 7.5. Now then, the units of K. The trick is that the units of K are not always the same thing. It depends on the overall order of the reaction. It depends on the units of rate. It's not like concentration. I mean, the units of concentration are always molarity. Okay, the units of K are going to vary depending upon the units here. So that's why we need to write our units on every single part here, because we need to look then at what cancels out what. So on the bottom of this reaction, we have molarity squared and molarity. So I'm going to go ahead and write this out on a separate place. So we have molarity squared times molarity on the bottom. And then on top we have molarity divided by seconds. Well, this molarity would cancel out this molarity. And that would be all that would cancel out. So what we're left with then is seconds inversed and molarity squared on the bottom. So what this would come out to be then, since that seconds is on the bottom of the top, it would also be on the bottom there. So we would write this out as molarity inverse squared times seconds inverse. Another way to write this would be 1 over molarity squared times seconds. That isn't the units that that's always going to be for K, just for this particular reaction, since we have a second order and a first order on the bottom, and we have a molarity per second on top. We wind up with these units. Whenever you're asked a question where you have to calculate K, you're going to get 1 point for this, and you're going to get 1 point for that. Almost always. Sometimes they'll give you 1 point for having the correct answer with the correct number of units, but you need to make sure you get these units correct, that you know how to cancel them out like this in order to derive those units. So what this means then, the K value for this particular reaction is 7.5 molarity seconds inverse times seconds inverse. So let's go ahead and record this up here. And now we're ready for part C, where we're going to calculate the overall reaction order. And the overall reaction order, this isn't as hard. So the overall would just be the two orders added together. And so since nitrous oxide was second order and hydrogen was first order, that means it's going to be 2 plus 1. Get out your calculators if you need them, but the overall reaction order would be third. Alright, so that right there is a rate law question in a nutshell. This is a pretty common setup for these questions where you calculate the rate law first, use the rate law to find the rate constant, and you use your rate law to also find the overall reaction order. We can also use these two pieces of information right up here to calculate the rate at any step along the way. Or if we know the rate, we can use it to find the concentration of one of these two as well. But this value right here, this K value, would be consistent for any experiment that's done, 1 through a billion if we wanted to, as long as the temperature stayed the same. So we could calculate the rate, the expected rate, for any reaction if we know the concentrations based upon that K right there, using this equation. Let's practice with just the orders real quick, because I assume that's going to be the trickiest part of this. If we want to take a look at a reaction here, so we have nitrous oxide again. This time it is reacting with Cl2. Okay, and what it's producing probably doesn't really matter. But we can look here then and figure out what the order of each of these different compounds is based upon our 3 experiments that we did and these initial rates that are given. So what is the order with respect to Cl2? So here's our Cl2s right there. And we're going to have to pick one where NO stays the same, but Cl2 changes. If we look at experiment 1 and experiment 2, NO stays the same, Cl2 doubles. So that would be a good fit then. And when we do that then, so we can see that the Cl2, that doubles, and then the rate over here also doubled. So then using our formula, the concentration doubled, raised to the x power, should equal a doubling there. So that means that x would have to equal 1, so it's first order with respect to Cl2. So then what is it with respect to nitrous oxide? If we take a look at experiments 2 to 3, the NO doubled and the Cl2 stayed the same. So that means we can use that guy right there, doubling, and that guy right there. So if we divide 1.14 times 10 to the negative 5th by 2.86 times 10 to the negative 6th, we get roughly 4. So it quadrupled. So when we doubled the concentration of nitrous oxide, the reaction rate initially quadrupled. So using our same formula, we doubled the concentration, and the reaction rate quadrupled. So that means that x would have to equal 2, which means that this is a second order reaction. And so then the overall order of this reaction would be a third order reaction. All right, this may seem real crazy at first, but I promise you will get used to it. Just practice this, ask questions when you got them, and then we'll be able to move on to other things, and pretty soon this will be a simple concept to you. I promise.